Assalamu alaikum wa rahmatullahi wa barakatuh. This is Muhammad Hashim Iyad Jabr speaking, and I am doing my paper review as a partial fulfillment for the course of Robust Control Systems with Uncertain Physical Parameters. The course is under the supervision of Dr. Moayed Almobaied. I chose a paper from the given sheet, which was a generalization of the Mikhailov criterion with applications. As we know, Mikhailov criterion states that the hodograph of a real nth order degree Hurwitz stable polynomial turns strictly counterclockwise and goes through n quadrants as omega runs from 0 to plus infinity. In this paper, we first give an analytical version of this criterion and then extend this analytical condition to the case of the non-necessarily Hurwitz polynomials. This generalization is shown to linearize some control synthesis problems in the sense that the set of stabilizing controllers is obtained as the solution set of a number of linear equations. Okay? Consider a real polynomial, x of s of a degree n. We say that x of s is Hurwitz if all its roots lay in the left half plane. The Mikhailov criterion is a test to determine if x of s is Hurwitz or not based on the plot of xj omega, for omega runs from 0 to infinity, and this is known the Mikhailov plot. The real polynomial x of s of degree n is Hurwitz if and only if the plot of x of j omega with omega increasing from 0 to infinity turns strictly counterclockwise and goes through n quadrants as it turns. So, the Mikhailov criterion provides a graphical method to determine the stability of the polynomial given. In this paper, we ask the question, does the Mikhailov plot give any information when x of s is not stable, not Hurwitz in terms of the paper? On the root distribution of x of s? The answer to this question is yes, as we will show in the next section. Let x of s have L roots in the left half plane and R roots in the right half plane. For simplicity, it has no roots in the imaginary axis. We get argument of x of j omega minus argument of x of j0 equals pi over 2 multiplied by L minus R. But how is that coming? The net change of the argument of x of j omega as omega runs from minus infinity to plus infinity is made up of the sum of L terms corresponding to the left half plane roots of each change by plus pi and R terms corresponding to the right half plane roots, each of which change by minus pi. The result now follows from the symmetry of the root distribution of the real polynomial x of s about the real axis of the complex plane. This generalization introduces functions to track changes, as the sine function shown below. Now, we state the result for the general case as the assumption is dropped. We will follow in the next slide an assumption and the proof of the general case. In other words, the formula given work if x of s has one or more roots on the origin or on the imaginary axis. Let x of s have many roots as in the imaginary axis shown above and have many roots on the origin. We will use properties of real polynomials to derive sign changes and the proof of the general case in the following slide. Let's move on. This is the main theorem of the paper. The first assumption given above says and introduces the sign function. Alright? Theorem 4 in the paper is the generalized Mikhailov criterion, GMC, for the general case. It extends the Mikhailov criterion to cases where the polynomial x of s may have roots on the imaginary or at the origin, as we said. Let the non-negative real zeros of the imaginary part I omega b 0 equals omega naught greater than omega 1 less than omega 1 less than omega 2, etc. With respect multiplicities ki for I goes from 0 to t and let omega t plus 1 equals infinity. If the degree of x of s is even, the number of the right half plane roots r and the left half plane roots l satisfy the following equation given in this part. Alright, let me just highlight that for you. I can't just highlight using the PDF file. Here I am. However, if the degree of x of s is odd, the formula slightly modified to the equation given below. The proof sketch is that the function x of s is rewritten to explicitly separate the contributions of the imaginary and the real x's roots by analyzing the behavior of x of j omega, particularly in the real and imaginary components. The theorem identifies conditions under which the root count in the left half plane versus the right half plane is determined. Special consideration is given to cases where multiple roots exist at the origin or at the imaginary axis. This generalization helps determine the stability of polynomials that are not necessarily Hurwitz, extending the traditional Mikhailov criterion. It is useful in control system theory, especially in computing stabilizing feedback gains, and this is an application used by the author of the paper. However, I will just concentrate on the proof and how it works. The application will not be explained in my presentation. Example on the general case, which is the generalized Mikhailov criterion, GMC. The example says, let x of s equals s squared multiplied by s plus 1 multiplied by s plus 4 multiplied by s squared plus 1. This is the polynomial. By extending this polynomial, we get s to the power 6 plus 5 multiplied by s to the power 5 plus 5 multiplied by s to the power 4 plus 5 multiplied by s to the power 3 plus 4 multiplied by s to the power 2. The next step is that we evaluate the Mikhailov plot. By evaluating x of j omega, where omega is the frequency variable, we get minus omega to the power 6 plus 5 multiplied by omega to the power 4 minus 4 multiplied by omega to the power 2 plus j in the parenthesis 5 multiplied by omega by 5 minus 5 by omega multiplied by 5 to the power 3. This is the real part and this is the imaginary part. This is the real part. This is the imaginary part of the given polynomial above. Alright? The third step is that we obtain the positive roots of the imaginary part. The roots of I of omega are, the positive roots are 0 and 1. How is that coming? This is This is 5 multiplied by omega to the power 5 minus 5 multiplied by omega to the power 3. If we factorize that by 5 omega to the power 3, we get 1. We get omega squared minus 1. How is that equals 0? We have omega to the power 3 is factorization, so we have 3 zeros shown here, and omega squared minus 1 has 2 roots, minus 1 plus 1. We only considered at the positive real roots, so we'll get 1 on this section. Thus, we have 0 and 1 as the positive real roots. By applying the criterion determines the difference between the roots on the left half plane minus the roots on the right half plane. Okay? By using sign changes of the derivatives of the real omega and the imaginary omega, we compute the following expression and we get that the answer is 2. Since x of s has 2 left half plane roots and no right half plane roots, the answer is true. It is stable. It is Hurwitz. Okay? Alright. The result of the last section explained can be used to derive some linear equations that characterize the set of stabilizing gains. The set of stabilizing gains for the control systems are given by the set of K according to the n plus m are even or odd. However, as I said in the previous slides, I will not go through the applications used in the paper. I will just focus on the generalization on the Mikhailov plot and explain it to you. The conclusion and the future work. A formula of for L minus R, L refers to the roots on the left half plane and R refers to the roots on the right half plane, appeared first in the first section for the case of polynomials with no imaginary roots and most one root at the origin. This formula, which is different from the one developed at last, was also used to solve the constant gain stabilization problem in the paper. The results given are transparent extension of the Mikhailov criterion, and this analogs to the extension of the Hermite-Peeler theorem reported in section 2 and used to obtain linear solutions to PID control problems in the third section that is not explained in my paper, but you can refer that to you. The results given here also permit a linear solution to fixed order stabilization and performance problems beyond the constant gain case. These extensions are still under study. And this is the end of the presentation for my paper. I hope that the generalization of the paper was clear for you and how it's done. Thank you very much for listening and see you in the next one.